Oh, good afternoon. There was some strange music. I don't know what we had there. Okay, we're going to continue on with portfolio theory. Even though this asteroid is coming, the asteroid 2 miles in diameter is going to pass close to Earth, relatively close. Let's go on with portfolio theory. Now, one thing that Leuenberger talks about, and everybody talks about, are short sales. Now, what are short sales? In a short sale, you sell stock that you do not own. You say, how can you do that? How can you sell stock that you do not own? Well, the stock is borrowed from a broker. And in fact, unless you tell a broker the broker you use for your stocks not to use your stocks in a short sale, it can be used in a short sale. Now, it's always a good idea to tell your broker not to use your stocks in a short sale. Short sales tend to drive down the price of the stock. So you sell the stock at, say, time 0 that you don't own, you borrow it, and then you return stock, say, at some future time t. And now you're betting that the price of the stock will go down at time t, by the time of time t. So you can buy back the stock for much less than you sold it for. And there are a decent percentage of short sales every day on different stocks. There are also some rules. We'll talk about that because we'll give a homework assignment on that. Okay, let's do an example, an extreme example. Short sales. Okay. And here we'll do Enron stock. Enron was an energy company that you probably heard of that went bottom up. Okay. Now, on the January 1st of 2001, the share price was equal to $83. And let's say that we short this at this time. In other words, we sell. Now, exactly 1 year later, at 1/1/2002, what happens? The share price now, since it was realized that Enron was really a house of cards, went down to 37 cents. And so we say, well, let's buy it back. Now, suppose you had shorted you were smart or lucky and in fact there were some hedge funds that did this short because they were suspicious about Enron and shorted $1,000 shares on 1/1/01 and covered your short we use the term cover when we return the stock to the broker. Position on January 1st of the next year, 2002. Okay, now let's see what we have here, what happened here. So we sold for $83,000. Since it was 1,000 shares at $83 a share on 1101, and we bought back for $370 on 1102. So the percentage profit, now here's a place where Leuenberger on short sales really has a kind of a strange way to do this. I would prefer to do it this way. Percentage profit equals the $83,000 that you got on 1101 minus the $370 that you had to pay to return the stocks over your $370, right? Because $370 is the only money out of your pocket. And we'll say times 100 for percentage. Okay, and this equals 22,332.4%, which is not a bad profit here. And in fact, some hedge funds did this trade, so they really made out like bandits. Now, maybe I'll tell you next time. Another good topic for a project would be on either there are two topics: on the history of hedge funds, and secondly on hedge fund strategies. On the history of hedge funds, there's a very good book. I'll give a complete reference the next time, called "More Money Than God." So it's a historical perspective on hedge funds. It's very interesting. So that's a great, that would be a great project for some group. Now, what else do we have here today? We have some interesting stuff, although the professor always says that. Now, here's the bad news. Let's do some homework here. Homework number 1. Okay. Let's have this due next Friday. Now, if people have to travel or have some other duties due to their jobs, we'll try to be as flexible as possible with these due dates. But typically, we'll try to have one homework per week. Okay, so we'll have two problems. Find the margin requirements on short sales, because you have to post a margin from some broker. In other words, you could take Shearson, you could take any broker you want, E-Trade or any broker. Now it says state your choice, state your source, and if from the internet or the web, provide a printout. Okay, 2, let's do define the uptick rule. And let me just say what it is. The uptick rule is that they had, in certain time periods, they have the so-called uptick rule, that you could only short a stock on a day when the stock price was up. Okay, because shorting a stock actually gives an indication that a lot of people are negative on that stock. And its history. It's been dropped and brought back a number of times. And say, of course, that's the uptick rule for short sales. I should have said that. And then 3, find the percentage of short sales for several stocks of your choice. You might look at stocks that have gone up a lot recently, and you could look at stocks which are relatively stable. The stocks that have zoomed up recently would be things like Tesla, car, and Netflix. The market is up a little bit today, usually on Friday, and that's another good topic. The topic is the day of the week effect. Typically on Friday, the market is up. But that's just statistically. That's not guaranteed. Okay. Now, let's talk about portfolios of stocks. You could think of these as risky assets. A little later, we'll mix both risky assets and risk-free assets, like treasury bonds or treasury notes. And as before, we're going to let lowercase wi equal the proportion of our portfolio invested in asset I equals 1 to n. And this is typically what Leuenberger uses the I. I would prefer to use the J, but let's use the I. Let's use Leuenberger's notation here. Okay. Then it must be true that the sum of the WI, I equals 1 to N, must equal 1. In other words, you must invest your whole budget here. Okay, and if there are no short sales, if there are no short sales, then we have the following, that WI must be greater than or equal to 0 for all I. Okay. And in fact, some mutual funds, the rules in the specific mutual funds say they don't have any short sales. Okay. Some people might think short sales are risky or are negative on the market, but they're not. They're just a way, purchasing a stock is a way to bet that the stock price will go up. Shorting a stock is just betting that the stock price will go down. Okay. Also, why don't, let's see, that's good. That's enough. So this is for no short sales. We get greater than or equal to 0. In fact, if we have a short sale on stock I, then WI would be less than 0. Okay. So where we are here. Good. Okay, now the portfolio return and rate of return and rate of return RP are just the weighted returns of the stocks in the portfolio. That is, we have that the portfolio return just equals the sum I equals 1 to N WI capital RI. And also the rate of return is just equal to the sum I equals 1 to N of WI RI. Okay. So it's just a linearly weighted, both of these are weighted here. Now, let's have a quick review on probability theory, which Leuenberger has in chapter 6 also. let's just call this probability basics. Well, let's not call it theory. I get worried. Okay, definition. A random variable and we usually denote this as little r period v period, is nothing more is a function that maps the sample space to the, and we'll call it real numbers. So for everything in the sample space, for every outcome in the sample space, a random variable gives you a number. Suppose we're talking about flipping a coin, and we say that one of the outcomes in the sample space would be a coin comes up heads. And suppose we win $1 when the coin comes up heads. So we say that's +1. And suppose we lose $1 when it comes up tails. Then we'll say that if the outcome in the sample space is a tail, then the random variables will be -1. Okay. Now what about the expected value? And this is all review of things that you probably had. So we'll say EX, so we'll talk about the expected value of a random variable X equals the sum I equals 1 to M, let's use an M instead of an N here, of xi, pi for a discrete random variable. Okay. Now, if we have a continuous random variable, we'll have an integral instead of a summation for continuous RV. Okay. Well, let's just do the discrete one. It's a little easier here, where pi equals the probability that that the random variable x equals xi. Okay. And also this pi has to have some properties. Pi must have certain properties. Pi, it must be true that pi must be greater than or equal to 0, I equal 1 to m, and plus the sum over all possible pi's must equal 1. Okay. So these are two things that we need for any legitimate probability here. For a discrete case. Now, let's do, we're going to review just a couple more things before we get into the portfolio problem. Now, Hulenberger talks about the properties of the expected value. And these you probably know, but let's go over them anyway. First, he says if x is a constant, you could say a known quantity, then the expected value of x equals x. Of course, if x takes on a certain value, and it can only take on that value, then the expected value of that has to equal that constant. And 2, if y and z are random variables, and again I'm going to cross my capital letters, and z are RVs, and alpha and beta are numbers, you can consider these constants. Then we have the following. The expected value of alpha y plus beta z equals alpha times the expected value of y plus beta times the expected value of z. Okay. Let me be this a beta here. Okay, finally, we have the following. We'll say if y and z are independent RVs. So you could think of like 2 specific coin tosses. They would be independent of each other here. Then we have the following, that the expected value of yz, y times z, is equal to the expected value of y times the expected value of z. Okay. Now, let's look at, we talked about expected values. Now let's look at risk. And typically we said that was measured by either the variance or the standard deviation. Now the variance of y we denote this by sigma y squared, and it equals the expected value of y minus EY, the mean here, squared. And so this is the so-called second moment about the mean. course, this is the mean here. Okay. And this is a measure of dispersion. Or risk. But we usually take the square root of sigma y squared. Okay. The square root of sigma y squared is the standard deviation. The square root of sigma y squared equals sigma y equals the standard deviation. Okay. Now, the reason we like the standard deviation is that it's in the same units as the expected value of y. The variance is squared, of course. It's in squared units. So it's nicer to have this look at the standard deviation, although we'll look at both of them here. Now, a different equation for the variance is the following. We could say the variance of x, and Leuenberger gives this. Sometimes it's easier to use this for calculation, equals EX squared minus x bar squared. Well, x bar squared is just the mean. Okay. Now, to measure how one RV, random variable, varies with another RV, let's say 1, another, we could say x1, RV, say x2, we define the covariance. And that covariance, x1, x2, equals sigma 1, 2, where we have the following. Okay, so this is how we designate it, and let's define it here. Let's define it right now. Let's say sigma 1, 2 equals the expected value of x1 minus x1 bar, the mean, times x2 minus x2 bar. Okay, so that shows how one random variable varies with another. In other words, if stocks and bonds are sometimes inversely related, we would say that we would see the negative amount there. Now, by symmetry, we have the following. If we have two stocks, 1 and 2, in our portfolio, then by symmetry, it must be true that sigma 1, 2 equals sigma 2, 1. Okay. In general, sigma ij equals sigma ji. Okay? So how 1 varies with 2 must be the way 2 varies with 1. Otherwise, we have something really screwed up here. Now, let's continue on. Talk more about the variance. Okay. We also note the following. That sigma 1, 1, suppose we just take the covariance of 1 with itself equals E x1 minus x1 hat times x1 again minus x1 hat. And this is what? This is the expected value of x1 minus x1 hat squared. And what does this equal? This just equals sigma 1 squared. So if I equals j, then sigma ij equals just the variance, sigma I squared, or sigma j squared. Okay. So the covariance equals the variance if I equals j. Okay. Now, let's see if we can't define the variance of a portfolio here. Okay. Before that, let's talk a little more about the covariance. If we have that sigma ij equals 0, then I and j, and what we mean here is xi and xj, sometimes we'll just say I and j, are uncorrelated. So if their covariance equals 0, they're uncorrelated. Now, if the covariance is positive, then xi and xj are positively correlated. And finally, if sigma ij is negative, then xi and xj are negatively correlated. Now, but one thing is that we can't tell how much they are positively or negatively correlated. Or positively or negatively correlated. Okay. Now for that, we need the correlation coefficient. And we'll call that correlation coefficient rho ij. Okay. Let's see if we can define that. We'll say the correlation coefficient say rho equals rho ij, typically, equals the covariance over sigma I times sigma j over the standard deviation of I times the standard deviation of j. Okay. Now, rho ij is always between -1 and +1. Okay. If it's -1, we're perfectly negatively correlated. And if it's +1, we're perfectly positively correlated. So this correlation coefficient really can tell us about the degree of correlation Because if you just have the covariance, you don't know exactly what that means. If I just give you a number for the covariance, you don't know if it's perfectly negatively correlated, suppose it's negative, or it's just a little bit negatively correlated. Okay. Now also we know that here, obviously, if rho ij equals 0, this implies that xi and xj are uncorrelated. So this will be very important, this correlation coefficient. Here. Okay, now, let's look at the variance of a portfolio. Let's derive the variance of a portfolio. Okay. A portfolio of two stocks. This is an of two stocks, and we'll call it X and Y. Sometimes we use 1 and 2, but let's just call it X and Y. Now the variance of x plus y equals what? Equals sigma x squared plus 2 sigma x sigma y plus sigma y squared. Okay. We haven't derived that yet, but I'll derive this. Okay. And let's, this is equation 6.4. Page 146. Okay. Now, let's introduce rho xy into this. So now we'll get the variance of x plus y. This is our portfolio variance, equals sigma x squared, the variance of x, plus 2 sigma x sigma y. Now, why don't we express this times, oh, this should be, excuse me, this is a mistake here. I'm reading the wrong thing. This is 2 sigma xy. That's the covariance. Sigma x sigma y times rho xy. Okay. Because rho xy equals what? Rho xy since rho xy equals what? Equals sigma xy over sigma x times sigma y. So therefore, sigma xy equals what? Equals rho xy times sigma x times sigma y. Okay? So now we introduce this into there, plus sigma y squared, okay? Okay, and we'll derive this shortly. Okay, now we can extend this to having n stocks in our portfolio. Extend this to having n stocks in our portfolio. We haven't derived it yet, but we will. Okay. Now, the expected value of the portfolio rate of return is easy. It's just the weighted I equals 1 to n Wi expected value of Ri. Okay, so it's just linear here. And Wi. Now, the portfolio variance is not linear. We'll say that sigma p squared equals the sum, double summation here, the sum I equals 1 to n, j equals 1 to n, wi, wj, sigma ij. Now remember that the covariance sigma ij, if I equals j, the covariance equals the variance. Okay, so let's break that out. So we can break this out to the following, equals the sum I equals 1 to n of wi squared sigma I squared. So it's the sum of these weighted squared variances plus, now we have the covariances, plus the sum I equals 1 through n, j equals 1 through n, and we also have that it must be true that I does not equal j, because if I equals j, we're in the first part with the variances. So it's wi, wj, sigma ij. Okay. Let's see how much more we want to do today. And if we want to use the correlation coefficient to express this using our correlation coefficient, what do we get? We get sigma p squared equals the sum of all the variances first, I equals 1 to n sigma I squared, this has to be wi squared, plus this double summation, over I and j. I equals 1 through n. J equals 1 through n. I not equal to j, okay, because this is where our covariances are. Now we'll say rho ij, wi, wj, sigma I, sigma j. Okay. So if we'll see that we can reduce this diversification diversification, we look at risk measured by sigma p as a function of the number of stocks. And in our portfolio. So we're going to see what happens with that, and we're also going to specifically derive this sigma p squared. And here we can reduce. Our result is that we can reduce risk by adding stocks. More assets or stocks to our portfolio. And this is exactly what mutual funds do. They have a large number of stocks that they manage. It would be very hard for us to manage a very large portfolio, plus we'd have a lot of transaction costs. This is also sometimes called the insurance effect. And insurance companies insure a lot of people, and the people, they're diversifying because people die of different things in the insurance company. Typically, they don't count wars, because then you have a number of people dying of the same cause. But in general, people die of different things. Okay, I hope you have a very nice weekend, and I hope it stays a little drier than it is in West Lafayette today. And we have that homework assignment. Also, I think today's lecture and Monday's lecture won't be put up on the blackboard until Tuesday, because both of our TAs are away. Okay. Well, thank you very much. See you on Monday.